Hello everyone. Today let us discuss about p-n junction. Before we go to the topic p-n junction, let us know the classification of materials based on their conductivity. So based on the conductivity, they are classified into conductors, semiconductors and insulators. Conductors, as we all know, these are the good conductors of electricity. They'll conduct the current very easily. Some examples are metals. So metals will conduct the current easily. Now coming to insulators, these are the materials which will not allow the current to pass through them. Examples are like wood, etc. Now semiconductors, these are the materials which are intermediate between conductors and insulators where they will allow the current partially. Some examples are silicon, germanium, etc. Now again semiconductors has classified into intrinsic semiconductors and extrinsic semiconductors. Intrinsic semiconductors, these are the pure semiconductors, whereas extrinsic semiconductors are obtained by adding impurities to the intrinsic semiconductor. The process of adding impurities is called doping. The process is called doping. So by adding impurities, we will get the extrinsic semiconductor. Again, this extrinsic semiconductor is further classified into p-type extrinsic semiconductor and n-type extrinsic semiconductor. P-type extrinsic semiconductor is obtained by adding trivalent impurities to the intrinsic semiconductor. So here P indicates the positive ions which are the majority charge carriers. So holes are the majority charge carriers in p-type extrinsic semiconductor. N-type extrinsic semiconductor is obtained by adding pentavalent impurities to the intrinsic semiconductor. So here negative ions, electrons are the majority charge carriers in N-type extrinsic semiconductor. This is about the classification based on their conductivity. Now this p-n junction. Coming to the topic p-n junction. The definition of p-n junction is, it is a silicon or germanium crystal, a semiconducting crystal, in which one half of it is filled with the acceptor impurities. So consider this is a semiconducting crystal, silicon or germanium crystal, in which one half of it is filled with the acceptor impurities. Here acceptor impurities are the holes, and one more half is filled with the donor impurities, which are electrons. This is the definition of p-n junction. Now let us know what happens to the p-n junction in the absence of external field, in the presence of external field. Now if we consider this as a p-n junction in the absence of the external field, so if we see these are holes are the majority charge carriers in p-type extrinsic semiconductor, and electrons are the majority charge carriers in n region. Now there are electrons, these are the minority charge carriers in p region, and positive holes are the minority charge carriers in n region. Now in the first point, in the absence of the external field, these positive ions in the p type starts moving towards the n region, and these electrons in the n side starts moving towards the p region. This is the first point. Now in the second point, after these positive ions move towards the n region and negative ions move towards the p region, they get combined. This is called diffusion. They get combined, and the minority charge carriers, these electrons in this p region, are left uncovered. These ions will get uncovered. They are not like negative ions will repel by the negative, so they are left uncovered. This is the second point. In the third point, this is the third point. In the third point, there is the negative ions, the further if the negative ions move towards this side, these are repelled by the negative minority charge carriers, and the positive ions are repelled by the positive ions present in the n region. So there is a negative potential developed in the p region and positive potential developed in the n region. This total potential, the developed potential, is called junction potential or contact potential. This is junction or contact potential, or we may call it as barrier potential also. This potential developed across the junction is called junction potential. Its value is different for different semiconducting materials. For silicon, the junction potential is 0.3 electron volt. For germanium, it is 0.7 electron volt. And this region is called depletion region. The junction potential region is called depletion region, and the thickness of this region, the thickness of this region is about 10 power minus 6 meter. The thickness of this depletion region is 10 power minus 6 meter. This is about the p-n junction in the absence of the external field. Now let us discuss the what is the effect of external field on the p-n junction. Now in the presence of the external field, the p-n junction acts as a diode. Diode, it is a two-terminal device which is used to conduct the current only in one direction. So when the diode is forward biased, then it conducts the current. When it is reverse biased, it prevents the flow of current through it. So in the presence of external field, it acts as a diode. Now let us see when it is what happens when it is forward biased and when it is reverse biased. When the p-n junction is forward biased, the positive terminal of the battery is connected to the p-type and negative terminal of the battery is connected to the n-type. So here like charges repel, always like charges repels and unlike charges attract. So here positive, these are the like charges, so they repel and these positive ions move towards the depletion region. Similarly, these negative ions are repelled by the negative charge, so they move towards the depletion region. So the width of the depletion region decreases. This helps in the flow of current. So in the forward biased condition, the diode conducts the current. Now if we observe the graphical section, let us take this is the voltage and this is the current. In forward bias, the current is measured in milliamps. Always the current in forward bias is measured by milliamps. So it increases gradually with increase in the voltage. This is the graph of the p-n junction when it is forward biased. If we represent it by symbol, this is the symbol of a diode. This triangle indicates the p side and this is the n side, and in forward bias it is connected to the positive terminal of the battery and n is connected to negative terminal of the battery. This is the direction of current flow. This is the forward biased condition. When the p-n junction is reverse biased, P region is connected to negative terminal of the battery and positive terminal is connected to N region. So unlike charges attract each other, these positive ions will move towards the edge, and here they are attracted, and even here also the negative ions will move towards the edge. So this depletion region width starts increasing, which increases the resistance. Here there is a high resistance, so there is no flow of current through these majority charge carriers. However, there is a small amount of current flowing in this diode, which is due to the minority charge carriers. Minority charge carriers carry the current. Minority charge carriers carry the current that is measured in few microamps. So the current in the reverse bias is due to the flow of minority charge carriers. If we see the graphical section of reverse bias condition, here also the graphical section, here this is the voltage and this is the current which is measured in, this is the voltage and this is the current which is measured in microamps. Here also the current starts increasing along with the voltage, but at certain voltage it starts suddenly increasing. That sudden increasing at particular voltage, that voltage is called breakdown voltage. That is called breakdown voltage. And in forward bias, the current starts increasing along with the increase in the voltage. This is for forward biased condition and this is for reverse biased condition. So this sudden increase in the voltage is due to two reasons. The first reason is because avalanche breakdown. This avalanche breakdown, when the diode is reverse biased, this minority charge carriers in P region are negative ions. These are repelled by the negative terminal of the battery, so they move faster towards the depletion region. They collide with the other atoms, and when they get sufficient kinetic energy, they collide with the other atoms and they form electron-hole pairs. Electron-hole pairs are formed. Further, after gaining still more sufficient energy, they even collide with other atoms and forms more electron-hole pairs, and the electron-hole pairs gets multiplied till the avalanche is reached. So this region, the flow of current is suddenly increases at a particular voltage. This is the avalanche breakdown. Second region is Zener breakdown. The second region for sudden increase in the current is Zener breakdown. Zener breakdown means when the diode is heavily doped, when this diode is heavily doped, then if we heavily dope the junction, then the potential depletion region decreases. This width of the depletion region becomes narrow and the electric field is increased, which creates the electron hole pairs, and so that the current increases gradually at a particular voltage. This is called Zener effect. This is called the Zener effect, which is discovered by the American scientist C. Zener. So hence it is called Zener effect. This Zener breakdown voltage depends upon the amount of doping. The breakdown voltage Vz is also sometimes called Zener voltage or knee voltage. Now we have Zener diode, which is a properly doped diode with a narrow breakdown voltage, is called Zener diode. Zener diode always works in the reverse biased condition. If it is forward biased, then it acts as a normal diode. So this is about the PN junction. Thank you.